So welcome everyone to Marco's second micro-school. It's also his last one. Marco's a visiting PhD student from Germany, where he's with the geography department, and he's working a lot with Earth observation data. And today he's going to be showing us how to unlock Earth observation data using Xarrays and ecosystem tools. It's a lead on from his last presentation, and I believe you'll probably have a Jupyter notebook or some notebook for us that we could follow along with. I know you did last time, which was quite handy. Otherwise, yes, please take it away, Marco.
Yeah, thank you for the introduction. And yeah, exactly, I have a notebook ready. I will share my screen. So this is it. I will also now share the link. So I've stored the notebook that I'm going to show here in a GitHub repository. It's also including the notebook from last time, from 2 weeks ago. I think someone has the microphone on, so it would be good if you could mute yourself. Chat. So yeah, I will go through the notebook. If you click here in the GitHub repository on notebook, you will it will lead you to a Colab notebook, and there you can just click and do it yourself after the recording if you want. But for now, you can just watch and listen to what I'm saying. So yeah, this is here just an introduction with some information. I have also linked the last school here as well. And as Sandra already said, I'm going to unlock Earth observation data. I'm going to show you how to access Earth observation data using Python code, which is nowadays quite important because the amount of Earth observation data is growing and growing, and in order to access and analyze this data, it's you cannot anymore just download these scenes or these data sets onto your local computer and then work. I mean, for a small scale, yes, but if you want to do an analysis on a bigger scale or with multiple data sets, it's going to get quite difficult. So I'm going to show you how to access this data from cloud repositories, basically. So some technology that is enabling this is something called spatial temporal asset catalogs. It's kind of a metadata specification, so that the data that is stored on cloud repositories comes with this metadata, and tools that I'm going to show here can access this information and provide this data in an efficient way. In this case, we're loading these datasets as Xarray objects. So this is why this talk is related to the last one, which was an introduction to Xarray. So just I had here an analogy just to kind of understand the different parts of this stack metadata specifications. It's just good to know that there's different levels in the hierarchy. So there's like a catalog and collections. The analogy is with bookshops and book and so on. You can read it later if you want. And also click here on these links, which kind of show you what is meant by that. Maybe I'm just going to, I will not click any links. It's maybe too much information. So we are going to load some main packages here, and there are different packages that you can use to load these catalogs and use Xarray objects. So odc-stac, for example, and stack are two main ones. I'm going to focus here on odc-stac, which is also a package that is used mainly by Digital Health Africa, which is also going to be shown here as an example. So we're going to go from 0 to DataCube. We're starting with step 0, which data product do we actually want and how can we access that? So I already mentioned Digital Health Africa. This is one provider of Earth observation data for the African continent. They also have a lot of additional notebooks and so on, so it's quite helpful. Another main repository or provider is Microsoft Planetary Computer. So I've provided here some information where, for example, you can get an overview of the data sets that are available. So this is for Digital Earth Africa. So for different topics, they have different data sets available. Also here, this, okay, I will show this quickly. It's quite handy. So here it's an overview of the data sets as well, but you can click on any of these and also see, like the metadata that is stored with this data sets, for example, and you can click around and explore a given data set. So it's quite, can be quite useful. So I'm going to, just save here the access point of this data catalog and one of the collections. So one data product, which is here the central one data set in the variable. And the next, so now we have decided, okay, what do we want? We want here central one data, and we know where we can get it. The next step is to define the spatial and temporal dimensions of our data cube, or the data that we want to load. So the temporal dimension is quite straightforward. We can just provide a temporal range in as two strings. So in this case, from the beginning of 2021 until the end of 2021. There's also different ways how you can provide this information. So I've given here some examples, but this is quite easy. With a spatial dimension, there's different options. If you know your area of interest so well that you can just type down the coordinates, that's great for you, but I cannot do that. So usually I have already a vector file that is defining my area of interest, so I can load that with also some Python packages like GeoPandas, or you can use an interactive tool. So GeoJSON.io is quite helpful that I have used in the past. So it's opening up a world map, and you can just zoom around and create your kind of a bounding box of an area, and it will provide here on the right side already like a code snippet with some coordinates. But you can also save this as a vector file and then load it with GeoPandas, for example, and use that in your analysis. Or you can use also in Python an interactive map. So I have here provided a small Python script that is just creating here in the notebook an interactive map. And I can also click around here and, for example, select a rectangle around Stellenbosch, where I am right now, and it will print out the bounding box coordinates. And these I can then use in the next steps to load the data that I want. Or I can here also click on a point, and it will also provide the coordinates. So it's quite useful. It's a very small script. So hopefully it's also useful for you. So we're defining here the bounding box coordinates, and we already know what we want, for what time range we want the data, and for which location. So there's already enough information to load data into Python. So here we're going to use a package called PyStack client. So this is useful for handling these stack metadata repositories. So we're first the catalog that we defined earlier, or like the endpoint to a specific catalog, and then we can search this catalog for the data that we want. So what we are defining here is a search query. We're defining the collection that we want. So this also I defined earlier. The data range and the bounding box. And when we run this, so I can do it again, quite fast, it will search the cloud repository for the data that we want, and it will print out here how many items it found. So one item is, for example, one scene. So just going to wait a second. Last time I ran it, it was a little bit faster, but well, anyway, I have already ran the other cells anyway, so we can just move on. So something is strange because I think it should just take 2 or 3 seconds max. So when we have these items loaded, or when we we retrieved the items that we want, we can load these into an Xarray object, so to create a multi-dimensional array, and then continue on with another analysis we want. So as I said earlier, I will show here how to do this using the package odc-stac. And I have, I can show later quickly also a bonus section where I'm showing a different option of how to load this, the same data. Something that's specific here to loading the Digital Africa data is this small snippet of configuration. This is relevant because the data is hosted on AWS, and yeah, they need this information. So I just copied it from the tutorial of Digital Africa, and I'm not going to worry too much about it. Then we are going to use from odc-stac a function that is called stack load, and this is then transforming or converting our data into an Xarray object. So we are providing here these items that I have here not finished, so 122 items that I am giving forwarding to this function. Also, well, just for to show something, I will comment this out. And I'm defining the bands that I want, data type, and so on. So both of these information, for example, you can get from the page of the data product. So, for example, for the Sentinel-1 data, Digital Africa has a in their Explorer, they have information about this data set. So each data set is stored differently with a different data type. And so on. So this is can be quite important. Here you have different measurements, for example, that have different names. Also between platforms, sometimes the names of these bands can be different. So this is something to take note and just be careful. If something doesn't work that you assumed is working, maybe you just made a small mistake in providing this information. So, so here it's saying which data type this data is stored, so this is important. And I'm just using that to forward that. Just going to run this again. And yeah, when we run this, it's creating a Xarray object, and you can see here, so these two bands are now available here as two variables. If I'm showing you this, it's showing a quite big data set. So there's now here 11 point something gigabytes, and the other variable as well. So this, I just wanted to show that even though we provided a bounding box earlier to find the items, when we load it without providing again this bounding box, it will load much more data than we want. The data is usually these data sets are like split into different tiles. So what we are seeing here is that the bounding box that I defined earlier, it's probably intersecting with 4 of these big tiles, and it's therefore loading much more data than we want. So if we provide this information also to the loading of the data, then this will be much smaller and much more easy to handle. Also, something that you might notice now is that this is quite fast. So before when I loaded all of the data for these 4 tiles, it was like 11 gigabytes, and this is quite a large data set. And this notebook, it doesn't have any like that much resources. So it's like 12 gigabytes of memory, for example. So how did we do that? We didn't actually load the data here into memory. We just loaded kind of a representation of this data. So tools are using the metadata that comes with Earth observation data to just understand the data type and how big it is and so on, and just showing a kind of a representation. And this is important here to know, especially if you're working with big data sets, that there's something called lazy evaluation or lazy execution, which means that the data is here like split into smaller parts, and the computation, for example, if you want to calculate the mean of this data set and plot it, then this is only going to happen at the end of this workflow, basically. So only when we execute, if we plot something, we need to know exactly the data that we want to plot. So in the background, then it will actually load the data into memory. But it's doing that by loading only small parts at a time, and that is quite powerful, because then we can kind of load a lot of data sets that are bigger than the memory that we have actually, and perform analysis. If maybe now the way I explained is a little bit confusing, you can read again about it here, and I also provided here some additional resources that are quite helpful to understand what this actually means. So just to show you this again, just to show you an example. So what we're doing here is we take this data set, we select one of the variables. So we're kind of chaining here different operations together. And if I execute this, this is also going to happen immediately, more or less, because the computation is not happening yet. But when I actually plot the data, then it's starting a computation because it actually needs the data in the background. So this is maybe a way to better understand what I mean with that. So here you can see our first Earth observation scene. This is mean for 1 month for the center of one data set, and showing here in the middle Stellenbosch. So I think time is slowly running out, so I just show you that here I summarized also the code that I now showed. So it's not that much if you think about it, just a few lines, and you can load an Earth observation data set from the data set that you want for a location that you want. So it's quite powerful. And just to show you that there's also different ways of loading that. So here is an example of using another package but you can just, if you were interested, you can go through this on your own. Here I've loaded another area, so maybe you recognize this Kebakulas. And also an example of how to use this package to load Google Earth Engine data. So this is maybe also interesting for some of you. Yeah, when after you load this kind of data set, you can work with Xarray and other tools that are related to Xarray and yeah, create your workflow, your analysis. So what I also wanted to show quickly is in the context of Earth observation, a lot of times you want to maybe create indices. So for example, with Sentinel-2 data, optical data, they have different spectral bands, and from these spectral bands you can create, for example, a vegetation index that is showing you the health of the vegetation. So there's a lot of different indices, especially for optical satellite data. And instead of having to yeah, create here a formula in Python, there's also packages that can do that for you. So one very helpful package is spyndex. And I'm just using, in this case here, I'm loading different data sets, so Sentinel-2, and showing you how I can kind of on the fly create two different indices from this data set. And yeah, so this can be quite helpful and also mitigates errors, because providing a formula on your own, you might do a mistake in the bands that you're choosing and so on. So this can lead to mistakes. So here this package is kind of yeah, providing all of these formulas, and you don't have to worry about it. Yeah. So this thing is it for now. I have also here another example, but I was not able to now provide it, but I will add it later on, just to show how to load a land cover data set and then use that to mask another data set, for example. So this is also maybe quite helpful. And some next steps, if you want to learn more about Earth observation fundamentals, I can recommend EU College, or if you want to get into analyzing Earth observation data for a specific application like agriculture monitoring, here these notebooks from Digital Earth Africa are quite helpful. There's a lot of examples. And with that, I end my presentation, and if you have questions, feel free to ask.
Thanks so much, Marco. There are a few questions in the chat that I'll read to you quickly. One was from Tussle, who asked about if you want to select the date range and filter some of the features from the data sets, you'll need to know the date format and the different data sets available. How do you find that info?
The date format, I mean, the format is kind of standardized, so you can use this kind of date format, and for loading the stack data, it will work. So even if maybe the metadata in the background is using a little bit different format, I mean, this is standardized, so I think this should not be a problem. And then there was another related question.
Yes, there was another question about whether or not Digital Earth has data sets for Europe. I did answer it in that Digital Earth Africa is for Africa, and I know that there is one for Australia, but as far as I know, there isn't anything for Europe. But Google Earth Engine then does supply for a global.
Yeah, yeah, exactly. Or Microsoft Planetary Computer, they are also providing data for Europe. I would like to, unfortunately, I cannot at the moment recommend maybe the European Space Agency's stack catalogs. I think there's still some issues, so they are slowly also moving to providing the data sets as together with stack metadata. But yeah, I was at the moment a little bit careful to recommend that. So yeah,
Okay.
but in the
And
future,
in the future, just keep your eyes open for the stack options across the other platforms.
exactly.
And then another one was, are there data sets for climate and weather as well? I did add in the link to Digital Earth Africa itself, but I don't know if there's a catalog of data there.
Back in here, I will show maybe quickly both of these catalogs. There is also climate data available here. I just have to look. Meteorology. So there's some, Era 5 climate grid data, for example, or rainfall estimates from chirps. I think Planetary Computer has a little more on that. So here is they have a nice here website to quickly go to different data sets. Some of these are, I think, only for North America, but there's also some for, like a lot of them also for the whole globe. So yeah.
Okay. Then Martin asked if you've tried it already with the Copernicus data space ecosystem.
Yeah, that was what I was now kind of referring to with the stack metadata. I have tried because I know that they recently, I think, added also a stack catalog or API to the Copernicus space data ecosystem. But I think there was some problems because if you go into detail, I think the assets, so the geotiffs for one scene, for example, they were not provided in the metadata. So these tools might have some problems with that.
Perfect. Then Gerald asked if the same approach would work using Dask.
I mean, actually, okay, I didn't mention that because it's a lot of information if you don't know all of these technologies. But Dask is used in the background, so Xarray and Dask are working kind of hand in hand, especially with this what I've shown here, lazy evaluation of this data. So here, so by using this one parameter for chunks, it will load the data as a lazy Dask-backed Xarray object. So Dask is used in the background. And for anyone who doesn't know Dask, Dask is a Python package that is for parallelization of Python code, basically.
Great. Then, are there any other questions? You can also just put your hand up when you speak. All right. If not, Marco is here for another month or so. He's sitting with us here at the Mathematical Biosciences unit in Stellenbosch, in one of the rooms here at the maths department. So I'm sure if anyone would like to chat to him, he'd be happy to chat. If you want to get in contact with him, Marco, your
info. I just wanted to mention, like, also if someone is watching this maybe in 2 months and I'm not here anymore, you're happy to also create an issue in my GitHub repository, and I'm happy to also answer questions there or help if something is wrong, not working anymore, for example. So that's that, or you can reach out to me here on different platforms that I've provided here in the notebook. Great,
yeah. So all that info is on Marco's GitHub site. So if you click on the link that he's provided and you just navigate to the GitHub, you can also get more information to contact him there. If there's nothing else, Marco, thanks so much for your time. I think we've learned a lot and opened our eyes to the world of X-arrays and how we can use it to access Earth observation data. And hopefully we'll have you back again, and hopefully in person sometime later on in your PhD, where you can give us a colloquium or something on your results.
Sure. Yeah, it was a pleasure. Thank you.
Thanks very much. All right. Cheers, everyone.
Thank you.